This is another part of my series where I help YouTuber Melissa Lucy get an A in chemistry this semester. Now, before we begin, make sure to download your free study plan, which includes different videos and resources that I personally recommend to help you get through this semester. The link is in the description box. All right, let's begin. I'm gonna bring back just the electron configuration that we had before with iron, which we found previously. So if I were to write this out, iron would have been 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. So with ions, remember, ions are just telling us that it's an element that has a charge. So this 2+ charge is going to change the electron configuration. And I want you to think of electrons, and we know that they're negatively charged. So if we were to have a positive charge, it's actually going to remove electrons. And then the opposite, if there's a negative charge, like sulfur in this case, that's actually going to gain electrons. So we're going to add more electrons.
Okay.
Yeah. So I'll say here just to note, positive charge, you're actually going to subtract electrons. And then negative charge, you're going to add electrons. So for iron, if I were to just rewrite everything here again, where we're going to remove the electrons, so we're removing 2 electrons. The place we want to remove it from is always going to be towards the end. Now, this is going to be really important to know where we're going to remove the electrons from. We're not going to remove electrons from, let's say, the 3D level, because that's already higher in energy versus something that's like 4SD. So like versus the S. You know, I'm looking at the S subshell and I'm comparing the D sublevel, S sublevel, D sublevel, and I know that the D sublevel has higher energy than the S. So that's why I'm not going to take it away from there. Does that make sense?
Kind of. I just always thought that like the energy levels went in order based on the number. No? It's based on like the letter?
It's more complicated than that. Oh. So I know. It starts off, yes. Like let's say if I were to compare like the 2p and the 4s, the 4s would have a higher energy level because it's far greater than since 4 is far greater than 2.
Right. That's what I was thinking.
But once we get to this portion, like towards the end, like those are kind of like similar, but what's going to make it is just the fact that this is at the D subshell or D sublevel. And then that's going to be a little bit more. So the D sublevel prefers to be either half full. So remember, D needs to be, or the maximum is 10 electrons. So half full would be 5. So it prefers to either be in this range between 5 to 10. Anything lower than that, and it's not stable. Okay, so that's why I would actually completely remove this portion. And our new electron configuration would have actually been this whole thing just minus that 4s2.
Okay.
So I would literally get rid of this. And this is my electron configuration for this ion.
Okay.
Cool. All right, same thing goes for the next one. What would I do if I'm now removing 3 electrons? So I'll still do the same thing where I know, okay, well, I can remove it from this 4s, level. So that's gone. But I still have one more electron that I need to remove. Where do I take it from? Now I can take it from this level. And that's still going to be half full. Like this would subtract 1, and now we're going to get 5. And it's still half full since it wants to be, either 5 and up. And it's still stable. It's still fine. So our actual electron configuration would have been this. Making sense?
Yeah.
Okay. We'll do this for sulfur. So I'm just going to write out what sulfur would have been just in its typical state here. Hold on. Okay. And then now that we have a negative charge, we know that we're actually going to add electrons. So we're adding 2 electrons. And then now in this case, the last like portion here of that electron configuration, that's going to want more electrons because it's not completely full. And we know like P, to be completely full, that's going to be at S. Sorry, that's going to be at S. It's going to be at 6. Does that make sense?
Yes, I think.
Okay, I'll say it again. I'm adding 2 electrons, so I'm adding 2 electrons to the end. And then the maximum amount of electrons that P can hold is 6.
Okay, so it'll be stable at 6, so that's what we would want to do. So what if that was already 6?
It wouldn't work.
Oh, okay, so that wouldn't happen.
That wouldn't happen.
Okay.
It'd be impossible.
Trick question. I wouldn't be surprised if it says like none of the above, you know? Yeah, not possible. We're not allowed to go past the maximum amount of electrons. Cool. Awesome. Then that's basically the main things for ions. Now these are exceptions. So there are always exceptions to the rules, of course. These are the ones I'd say to definitely know. The first 2, chromium and copper, are probably the most common trick questions I have seen on electron configuration. So you may be asked like, hey, write the electron configuration of chromium. And you would expect it to be this, but that would be wrong. And the reason for that, it's more complicated, I would say. It's nothing that you necessarily have to know for this class. The actual electron configurations are found experimentally. Like I said, I don't expect you to even know any of that. Don't worry about that. But just knowing what the exceptions are, that's important. So these are basically the majority of the ones that I've seen. But like I said, these 2, most common ones. Okay, so if you're going to know any of these, know those first 2. That the actual ones are these.
Okay, so memorize the actual ones, you think?
Yes.
Okay.
Yeah.
Cool. I mean, another little thing to kind of like explain why is still going with the same concept that like this is actually not half full, right? Remember, we wanted it to either be D5 or D10 or something in between. And because this is 4, that's why it's not going to be stable. And it takes 1 electron from this and it goes up to 5. And then same thing here, like, oh, this is so close to being completely full. So it's going to take 1 electron here and now it's stable.
Oh, okay.
Yeah, that's the reason behind these really. But there's more. Don't worry about it.
Yeah, that's just weird because it's like, well, then you didn't fill the S all the way, right? Like,
right, but we want to fill the highest energy orbital first. Or not first, sorry. Last, but we want the highest energy orbital to be half full or full.
Okay. So you're saying because the 3 is before the 4?
No, because of the D sub-level. So the D sub-level is going to be higher in comparison to 4S. And if I were to go back here, 4S, 3D, they seem like they're almost exactly the same. I'm going to move them up just a tiny bit, just so you could actually tell. But 3D is actually higher up in energy, like by a little bit, from 4S.
Okay.
That's why.
Okay.
Cool. All right, last thing. So we could also determine the overall core electrons and valence electrons just by looking at the electron configuration. And as you can tell, I already highlighted everything. The way we can do this for valence electrons, and you should have gone over what valence electrons are, but I'll go over it. That just means that they're the outermost electrons. Like think of the atom, like your nucleus and like everything that's in there. Actually, let's just not go to biology here. Let's just say our protons. Let's say our atom is there. Protons, neutrons, right? That's what's in the middle. And then it's surrounded by electrons.
Right.
On these orbitals. So your outermost shell is basically this. Like that's where your valence electrons are. So that's just what it's meant. Knowing that definition can be important.
Does that relate to like the electrons having to fill the inner shell first, or like is that the same thing before they can go to the outside? Oh, okay.
Yeah, it's a little bit different. I'd say it's more on just like putting a label to which ones, do different things. Valence electrons are going to come back in a later chapter, and like we'll actually be drawing the structures and like what molecules actually like look like on a 2D level. And we'll be using valence electrons for that. But for now, it's just like, okay, we have these two different things. They're used for they're used for forming different compounds or forming different molecules. So don't worry too much about it right now. We will go into more detail in the next few chapters.
Okay.
Yeah. But for now, just knowing that they're on the outermost shell, that's what's important. How we find them looking at the electron configuration is by this way. So we're going to look at the actual like n value or integer. So 4, and we look at the highest. So we're going to look at the highest n value, which in this case is 4. And then we're going to add those electrons together. And that's where I got 4. So like if we had only, 5s2, and that was the highest, then my only valence electrons would have been 2.
What do you mean the highest? Like because 4 is the highest?
Yes.
Oh, okay, I see.
Yeah. And then like if this were a 3, then the valence electrons would have been 5.
Okay, I see. So, yeah. Okay, yeah, that makes sense. So if the highest was like the 3, then we would count up the electrons of all the 3s?
Yes.
Okay.
Exactly.
And then everything remaining would then be the core electrons. That's just what's inside.
Okay.
In the next video, we're going to go over several practice problems. So be ready to try those out.